Hey, hello guys. Today we're gonna discuss about matrix addition with unified memory in CUDA. This presentation explores matrix addition using CUDA's unified memory feature. We will examine the implementation, performance consideration, and impact of using memset operation in this context. Unified memory in CUDA. Simplified memory management, automatic data migration, ease of programming. Unified memory creates a single address space accessible by both CPU and GPU. The system handles data transfer between host and device memory automatically. Developers can focus on algorithm rather than explicit memory management. Next, we're going to discuss about matrix addition algorithm. The steps follows: initialize matrices, perform addition, store result. In initialize matrix, allocate and populate matrix A and B with random float values. Add corresponding elements of A and B to create matrix C. Then save the result matrix C in unified memory for access by both CPU and GPU. CUDA kernel implementation, thread indexing, boundary check, element-wise addition. Calculate global thread indices based on block and grid dimensions. Boundary check, ensure threads only operate within the matrix dimension. Element-wise addition, perform addition for the matrix element corresponding to the thread index. Memory allocation with unified memory. First, QDOC malloc management function allocate unified memory for matrices A and B. Then data initialization. Populate matrices A and B with random data using initial data function. And finally, kernel invocation. Launch CUDA kernel to perform matrix addition on unified memory. Impact of memset operation. With memset, we can initialize memory to 0, additional time overhead, and ensure consistent initial state. Without memset, leaves memory uninitialized, slightly faster execution may contain residual data. Performance analysis. Execution time. Measure kernel running time using CUDA events or host side timing functions. Memory bandwidth. Calculate effective memory bandwidth to evaluate data transfer efficiency. Profiling tools. Use NVProof or NVSite for detailed performance analysis. Optimization strategies. Collapsed memory access. Ensure thread access contiguous memory location for efficient data transfer. Shared memory usage. Utilize shared memory for frequently accessed data to reduce global memory traffic. Accompany optimization. Adjust block size and register usage to maximize GPU accompany. Asynchronous operation. Overlap computation with data transfer using CUDA streams. Okay. In this code, the first thing you will notice is some error checking macros. These help us catch any mistakes when we are calling CUDA functions, which is super useful because it gives us detailed error messages if anything goes wrong. Next up, we got a few helper function. Initial data. Initial data. Initial data fills our matrix with some random values, while some matrix on host perform matrix addition on the CPU. Then check result helps us verify that our GPU computation matches what we get on the CPU, so we know everything working as expected. The real magic happens in GPU kernel, some matrix GPU. Here, each GPU thread handles the addition of one element in the matrix, so we can do a ton of addition simultaneously, taking advantage of GPU parallelism. It's effective, fast, and perfect for tasks like this. In main function, we start by setting up our device and initializing matrices. We allocate memory using CUDA malloc management, which gives us unified memory between the CPU and GPU. This makes it easier to share data across them without manually transferring memory. Once we have initialized everything, we time the matrix addition on CPU and then on GPU to compare speeds. Finally, we check the GPU result, free up space, and reset the device. By offloading heavy computation to GPU, we get a big performance boost. If you're working with large data, understanding CUDA and parallel programming can open up so many opportunities. Then we are diving into CUDA program that performs matrix addition on GPU but without using memset for initialization. Let's walk through some of the important parts here. We start with error checking macros as same as above, which are crucial for catching CUDA errors. These macros helps us diagnose any issues quickly by outputting error codes and messages. Next, our sum matrix GPU kernel function calculates the sum of two matrices leveraging the GPU parallel processing capability. Each thread computes the sum of one element, allowing us process large matrices much faster than non-GPU. In main function, In main function, we set up matrix dimension and use CUDA malloc management to allot memory with unified memory management, which make it simpler to handle memory across CPU and GPU without manual copying. After some initialization, we launch our kernel, we warm it up with a small size, then execute the full addition. Finally, we check the results for accuracy. These are the output we got with program with memset and without memset. We can see the result as the program has executed by using unified memory. It is observed that removing memset function has given more 0.106563 seconds time. Here we came into conclusion and future work. Unified memory benefit simplifies CUDA programming while maintaining high performance for matrix operations. Memset consideration. Removing memset can improve performance but may introduce inconsistent in uninitialized memory. Future exploration. Investigate advanced unified memory features and their impact on large matrix operations.